Imagine, if you will, standing on the edge of infinity gazing into the abyss of time. It's dark, cold, and silent until in a flash brighter than 1,000 at Las Vegas strips, the universe bursts into existence. This is the Big Bang. 13.8 billion years ago, the cosmic kickoff that sets everything in motion. From this explosive birth comes all the matter and energy that will ever be. Particles collide, atoms form, and stars ignite like fireworks on the 4th of July. These stars are the alchemists of the cosmos, fusing light elements into heavier ones. Carbon, oxygen, iron. The building blocks of planets of life, of you and me, right here in the good old USA. But let's fast forward through the eons. Stars live, die, and in their death throes they explode as supernovas. One such supernova, perhaps 5 billion years ago, sends a shockwave rippling through a vast cloud of gas and dust. Gravity, that relentless force, takes hold. The cloud collapses, spinning faster, flattening into a vast disk like a pancake on a griddle. At the center, density builds, and our sun is born. A blazing G-type star consuming 99% of the nebulous mass and sending out solar winds. What's left? A protoplanetary disk, a ring of dust and gas where planets will form. This is the nursery of our solar system, where temperatures vary dramatically, scorching near the sun, freezing far out. Closer to the sun, rocky particles condense. Beyond the frost line, ices form, leading to the gas giants Jupiter, Saturn, Uranus, Neptune. Accretion begins slowly. Dust particles, microns small, bump into each other in the disk. At low speeds, they stick together through electrostatic forces, growing to pebbles, then centimeter-sized rocks. As they get larger, gravity kicks in. Planetesimals form, bodies 10 to 100 kilometers across. The disk is now a swarm of these, orbiting the sun in elliptical paths, occasionally colliding. Some gentle mergers add mass, others shattering into fragments that get recycled by survivors. In the region that will become Earth's orbit, one planetesimal starts to dominate. We call it Proto-Earth, a growing embryo about the size of the Moon at first, then Mars. Every impact releases tremendous energy, melting the surface into a magma ocean. Radioactive elements decay and add more heat. Proto-Earth is a hellscape, glowing red with lava seas hundreds of miles deep, volcanoes erupting constantly. Once a protoplanet reaches a certain size, it enters runaway accretion. Its gravity dominates, pulling in material faster than competitors. Proto-Earth wins this race, growing to nearly its current mass. But the solar system is still crowded. Dozens of Mars-sized protoplanets vie for space. Orbital resonances with Jupiter destabilize paths, leading to more collisions every few thousand years. About 4.51 billion years ago, a rogue protoplanet named Theia enters the picture. Theia is Mars-size, formed perhaps at a stable Lagrange point, but perturbed by Jupiter's pull. Its path intersects Proto-Earth's. The collision is inevitable, but the angle is key. Not head-on, but a glancing blow at about 45 degrees, speed 4 kilometers per second. Theia slams into Proto-Earth with the force of trillions of atomic bombs. Theia's iron core plunges into Earth's, merging and sinking to the center. The mantles vaporize and eject into space, forming a synestia, a torus-shaped cloud of molten rock and gas hotter than the sun's surface. Debris orbits Earth, a ring of fire extending thousands of miles. Debris orbits, particles collide and stick. Will this debris dissipate, leaving Earth moonless? Or will gravity weave its magic? In the ensuing chaos, small moonlets form first, then merge. In mere weeks to months, the bulk coalesces into a single body, our moon. Initially orbiting much closer, born from the fiery remnants of that colossal smash-up. The impact tilts Earth's axis, giving us seasons, speeds up rotation, shortening days to just a few hours at first. Gravity takes over in differentiation, heavier iron and nickel sink to form the dense core. Lighter silicates rise to the mantle and crust, generating our magnetic field, the invisible shield protecting us from solar winds. In the aftermath of the Theia impact, Earth is a glowing orb of molten rock, radiating heat like a blacksmith's forge. Gases released from the melting rock, water vapor, carbon dioxide, nitrogen, form a primitive atmosphere, but it's toxic, thick, hazy, and scorching. Comets and asteroids continue to bombard the planet in what's called the Late Heavy Bombardment, about 4.1 to 3.8 billion years ago. These impacts deliver water and organic compounds, seeding the ingredients for oceans and life. As Earth cools, the first solid crust forms. It's thin, fragile, constantly recycled. Rain from the condensing atmosphere fills basins, creating the first oceans. But these aren't the blue paradises we swim in. They're acidic, hot, and full of dissolved minerals. We call this earliest era the Hadean Aeon, named after Hades, the Greek underworld, fitting for a world of fire and brimstone. Temperatures drop from thousands of degrees to something more bearable. By 4.4 billion years ago, ancient zircon crystals show oceans existed, even continents starting to poke up. But could life emerge in this inferno? Scientists think yes, around hydrothermal vents on the ocean floor, black smokers spewing hot, mineral-rich water. Here, in the darkness, chemical reactions might have sparked the first self-replicating molecules, RNA perhaps, leading to primitive cells. It's the dawn of the Archean eon, about 4 billion years ago, when single-celled organisms begin to thrive, eventually producing oxygen through photosynthesis. That oxygen buildup, the Great Oxidation Event around 2.4 billion years ago, transforms the atmosphere from methane-rich to oxygen-rich, paving the way for complex life. But that's a story for another time. Back to formation. Earth's core, still hot from radioactive decay and leftover impact energy, drives convection in the mantle, kickstarting plate tectonics. Continents drift, mountains rise, oceans deepen, shaping the dynamic world we live on. Now, why does this matter to you, sitting in your living room in Texas or hiking in the Rockies? Because every atom in your body, carbon in your cells, iron in your blood came from those ancient stars and collisions. The Grand Canyon, carved from rocks forged in Earth's fiery youth. Hurricanes brewing over the Atlantic, powered by heat from the core, a remnant of that primordial melt. Scientists piece this together through moon rocks from Apollo missions, meteorites that are leftovers from the solar nebula, and computer simulations that replay the chaos. But mysteries remain. Where exactly did Earth's water come from? Asteroids, comets, or baked out from the rocks themselves? And was Theia the only big hit, or were there more? So, there you have it, the epic saga of Earth's birth. From a speck in a nebula to the vibrant planet sustaining billions of lives. It's a reminder that our world wasn't handed to us perfect. It was forged in fire, tempered by time. Next time you watch a sunset or feel the earth under your feet, remember, you're standing on the survivor of cosmic battles, a testament to the universe's creative destruction. If this story hooked you, imagine what else the cosmos has in store. Share this with a friend, hit that like button, and subscribe for more mind-bending science adventures. Until next time, keep looking up and wondering.